Good morning again. So we are here for a real treat. We have an excellent talk here by Professor Laurent Najman. He did his PhD in applied mathematics from Paris-Est University, and then he worked in a variety of places. One of them is Central Research Labs of Thompson, CSF, and where he was the Director of Research and Development. And he also joined the animation science, where he did excellent work that won him some of the best prizes and awards, one of them being the European Information Technology Prize in 1997 and the Hottest Products of the Year in 1996. And then he actually worked with OCE Print Technologies, where he did various problems on image analysis dedicated to scanning and printing. So as you can see, he has a vast, diverse set of expertise that he's going to draw from on this talk, and I hope you all get a lot out from his wisdom. He's currently a professor in the informatics department in ESIEE, and his research interests are in discrete mathematical morphology and discrete optimization. And today he's going to talk on morphological filtering in shape spaces. And with that, I welcome Professor Najman and to share his ideas with us.
So, another important reason to be happy is that there are few countries in the world where mathematical morphology, my main research field, has taken deep root, and Brazil is arguably one of the largest and the most important one. So I do expect that most of you, if not all, knows some basic mathematical morphology as dilation and erosion, which in a sense for me is reassuring. If you do not know what is a dilation, this is not a problem. I expect you to understand my talk. But if you do know what a dilation is, at least we share some common knowledge, and I can start from that. So the motivation of the goal today is image filtering and how to obtain such a result from a given input image. What you can notice here is that we remove from the input image everything that is not round. So it's a kind of erosion, or I don't know, filtering, in which you preserve the shape of the object, the shape being defined in a quite loose way by an energy function or an attribute or something like that. So intuitively what I want to do is to work with structuring elements, as in mathematical morphology classically, but being able to deal with structuring elements that do not have a fixed shape and to obtain such results. Okay, so the plan of the talk is the following. The route are taken into connected filtering. So I will first describe what connected filters are, and then I will describe the novelty, which is shape-based morphology. And then I will illustrate the work with various images taken from different applications before concluding. So first, connected filters. So one interesting direction in research is to try to find alternative representation to what an image is. The most classical one, I believe, is Fourier transform, functional decomposition, in which from a given image, this one is better, I think, because both sides you do have the mouse. So you have the phase and the amplitude, and you can analyze and find easily in this other representation of the image, equivalent representation. Some artifacts are present, some things are can be easily found in this image, its representation. But there are plenty of other. We can think of multi-resolution decomposition, looking at an image at various sizes, for example, or multiscale, in which you're trying to give for it a pixel, a region around it, according to a scale, but each pixel has different scales to which you can look at it. Or the representation that we will deal more specifically in this talk are the last two ones. So this is threshold decomposition. Threshold is the most basic operation in image analysis, I believe. So you take the whole stack of threshold. And hierarchical representation by grouping pixels according to some rules from the pixels themselves to large regions, the higher level in the hierarchy being the whole image itself, just one region. Okay, they are all very good representation, and you can mix them, you can do whatever you want with them. The choice is driven by the application needs, and you can do whatever you want with those. This is not the problem here. Okay, so what I'm going to look at are connected filters. Connected filters are filtering tools that merge flat zone with the same color or the same gray level. The main properties are they do not introduce new contour. When merging flat zone, you just remove contours, but you do not change the position of the contour, so the contour will be exactly the same before and after, maybe less contour in the results. One example is the leveling. It's the leveling preserve order between neighboring pixels. So if the center pixel is greater than a neighbor, you will have the same in the results. Well, it's not correct here, but not a problem here. The formula not correct here. But anyway, on this example, for example, you have the red function in F and a marker function H, and what you want to do is simply removing some blobs that are not marked by the H function. So you have remove a white blob and a black blob here, and preserving everything else in the image. And basically, well, this is just an example, but we're going to see how to implement and to deal with those kind of filters. One popular implementation relies on a tree representation, and there is a nice review that appears in Signal Processing magazine recently. Well, you start from the image, you build a tree from it. For example, the tree of, well, we're going to see exactly what kind of tree you can build on this image, but the tree is equivalent to the image. That's the important point. From the tree, you can reconstruct the image. And then you do the filtering not on the image itself, but on the tree. So you remove some nodes of the tree, so you obtain a second tree, and you reconstruct the image from this simplified tree. Okay. Here is one example. So it's a 1D signal here. You have on the x-axis and the y-axis, F. So the signal is in blue. Okay, you can take a threshold. At a given threshold, you have two connected components in red. Okay, very good. You can vary the parameter of the threshold, of course, and you can obtain a tree from that. Okay, you at altitude 5, you have this connected component. For these two connected component, 3 these two connected component, 2 this connected component, 1, okay, and 0. So plenty of connected components. The nice thing is that this connected component, well, they are either disjoint or nested. So you can build a graph from this connected component, actually a tree. The edge that you've added here, that we have added here, they represent the father-son relationship, the inclusion relationship. If you have an edge, that means that one of the node is included in the other. So this is a tree here. Okay, there are plenty of trees that we can build from the image. We've just seen the max tree. On this image, this example here, the max tree is very simple, just a straight line. But the tree of the minima is a bit more complicated. You have two minima, D and E, in black, at altitude 0. And, okay, one root. Another interesting tree is the tree of shapes that you can imagine as a tree of level lines. You just draw all the level lines, and for example, the level line of B include these two connected components here. So the shape of B is B union A union E, and you can do that, you obtain another tree. So you can think of it as a tree of level lines. With respect to these two trees, it's an autodual tree in the sense that you don't, you process black and white in the same sense. Here, the two leaves, in this tree, the leaves are either maxima or minima. Here, the leaves are both minima and maxima. But you can generalize and take any kind of merging tree. Here, it's a binary partition tree. You just divide your image according to some kind of superpixel, and you merge them according to some rule, whatever, and you have a true representation of your image. Very classical. Okay, is that clear? Please, if you have any question, don't hesitate to ask during the talk. So, once you have the tree, what can you do with that? You can filter, and to filter you need a rule. So here it's an attribute. For example, I take this connected component in red. What can you imagine? Plenty of things. For example, nice sound. I don't know how you do that, but here it's the area, simply the number of pixels of this component. You can have the 8, the difference between the highest pixel and the current level, or the volume, the number of pixels contained in the connected component and in the shape of the function itself. 3 attributes. And okay, these 3 attributes, they are increasing in the sense if the connected component is included in another component, the attribute of the first one is lower than the attribute of the second one. But in general, most shape attributes, they don't have this property, which is very nice, but unfortunately most of shape attributes don't have this property. So other attributes are, for example, kind of circularity. Circularity is the area divided by the p times the square, the length of the contour. So that's one for a circle. Or round object can be also found by the first attribute. You can also look at elongation, like taking for example, you take a best fitting ellipse and you measure the differences. You estimate the ratio, so that gives you a measure of how long an object is. Okay. They are not increasing, but they are very interesting. Okay, if you have an increasing attribute, it's easy to filter. Why? Because it amounts to remove the components you don't want. For example, if you want to remove every connected component with a volume of lower than 5, okay, you have 2 here for this component. Here 3, 2 plus 3 is 5. You will remove this one and this one also, and okay, you remove. So it's easy. It's just you remove the connected component from the tree. There is an example. It's a real example, part of a big application. This is ancillary, a kind of ancillary cells with small things that move, and they are responsible for the placement of the organs in the body. And in some rare disease, the cells don't move, and you can have the heart on the other side of the body and give you problems. Well, anyway, if you look at the maxima of the first image here, you have plenty of those maxima, but you can filter the image with volume criterion. You don't see much difference, and there are not so much difference, but actually this is a very good simplification steps are the maxima of this image. This is a good pre-segmentation at least. So very good filtering tool. The question is that if you want to process a non-increasing attribute, you don't know how to do that. Well, people have, well, yeah, not yet. If an attribute is increasing, you just prune the leaves. It's just threshold the attribute. But if you want to deal with non-increasing attribute, you have several routes that amounts more or less to threshold, either by removing the whole branch according to a rule. If you don't want a node at a given level, you remove also all the sons, all the branch to which the nodes belong, according to some rule. You can do simple thresholding strategy, also removing the nodes that you don't want by thresholding, but as we'll see later, it's not very convenient in some cases. What we'll do is a bit more elaborate, and this is the most important point in the talk. So wake up. Because I will reapply the same process on the graph. So generally, this is where people get confused, because from the tree, I build a tree. Hey, what's happening here? Well, you can see the tree as a graph itself. It's a graph. And you can value the tree, the node of the tree, with whatever you want, whatever kind of attribute. Well, it's in that case, you have a graph with neighbors. The neighbors relationship is simply whether you are a son or a father, so parenthood relationship, and give you a kind of neighborhood. So once you have this kind of neighborhood, you can apply any kind of graph algorithms on that tree, on that graph. So you can build a tree on the first tree. I will show you some example, but that's mainly the most complicated point. So, and this is how we do shape-based morphology. Okay, here is a very simple example, a tree in which you have nodes, and the nodes have an attribute that is whatever you want. It's not increasing. So in this tree, you can threshold this graph. So here's the connected component at level less than 4. There is only one node. At level 5, there is 2 connected components. At level 6, the node G merge with the node C, and you still have 2 connected components, but this node has merged with his son. And so you can continue. At level set, you have this node here, and so 1 connected component, and 8, and so on. So from the connected component, you can build a second tree. Take the mean tree here. So here, the component G merge with C, F and C merge with H, and this is only the resulting node. Here it's H is H union C, union G, union F, and so on. Is that clear? Because I can go on this a second time if you want, because this is the most complicated part. I will do that. So you are just building a tree of minima on a graph. This graph happens to be a tree, but you don't care, you just see as a planar graph here in this case. So the 2 leaves here, this is the connected component below 5. This will be the leaves of the tree, and G is contained in G union C here, and then in this tree, and so on. Okay? What have I done here? I've transformed the first image into a graph. Whatever is this graph. Here I will work only with trees, but this graph is a tree, okay? And then all the algorithm I'm dealing, the graph is equivalent, this tree is equivalent to the first image. So that's fine. With this tree I can reconstruct the image, but I will not work on the image space, I will work on the tree of shapes, because each node is a shape. So they are organized in a shape space. The relationship, neighborhood relationship, is the parenthood relationship, and I will work on this space of shapes to do things. And the first things I'm going to do is simply reapplying the same process in the space shape, in the shape space. Clear? Okay. This is good because it generalizes the classical attribute filtering. If the attribute is increasing, the mean tree of the first tree is the same, exactly the same tree. So you don't have to ask the question whether or not the attribute is increasing. You don't care. You just apply the process, whatever it is, and you don't change anything if the attribute is increasing. So you do work that is not useful, but you're doing what's usual. You can also find the attribute thresholding, because attribute thresholding is simply finding the leaves. Pruning the second tree is simply attribute thresholding. But you can do shape filter on the second tree, and in this case you obtain nice filters. Meaning that the transform, if you work with a max tree, you preserve the infimum relationship, so it's a lower leveling. If you work with the mean tree, the tree of minima, of minimum mean threshold, you preserve the superior relationship, so it's shape-based upper leveling. This has never been before. This is the first time I'm showing that. And if you work with a tree of shapes, this is a totally new kind of filter, because this filter is auto-dual, meaning that you process black and white in the same way, and it's self-dual, okay? And it's not anymore leveling, because you don't guarantee anything before and after, but it's a connected filter, and we call that kind of connected filter morphological shaping, which is, I like this word, morphological shaping, it's shape. Well, anyway. Okay, how do you use that? Here is an energy function here, where you have A, B, C, 2 minima, that you can order. Here, for example, A is lower than C and lower than B. This order is arbitrary, it depends on what you want to do. What I choose here is finding the altitude, and I say that a minimum is lower than another minimum if the altitude is lower. But you can choose other criterion. And so when you filter, for example, you can compute the altitude of this minimum, and you say that B will merge with C, and then C will merge with A, because it will merge with the phasor. So at this altitude, when you imagine you fill the image with water, at this level of water, here, the basin of B is filled, it diverges in C, so it merges with C. You continue to add more water, and then C is going to A. Okay. So you can attribute an 8 to each one of those minimum, and that give you a second attribute to filter the tree and preserve the blobs that are the most meaningful. So B here is less meaningful than C, that is itself less meaningful than A. Here I've used as attribute the altitude, the height, but you can use, once again, any kind of attribute on that second tree. Is that clear? Okay. So first application to object segmentation. Well, this looks like very complicated. It's a bunch of formulae, but actually it's very simple in principle. It's an energy that is more or less inspired by Mumford and Shah or Snake's energy. You have 3 terms in this energy. Here, this V here measure how different you are from the mean of the function. So here, these terms, here it's simply the variance. Here it's kind of variance of variation. And here, these terms tells whether you prefer to merge these 2 regions, take the union, or keep them separated. Here, it's simply a term that say that you want something more or less with more or less curvature, more or less agitated. And here is something to prevent small objects. But basically, that's Mumford-Shah energy. Okay. It's very complicated to optimize such a kind of energy, of course, because it's not non-convex. But well, nice thing is that you can do that quite easily if you look at your trees. So, okay, here it's the energy in a branch of the tree. Starting here, that's the leaf, the pixel itself. Here it's the root of the tree, and you can see how the energy behaves along the branch of the tree. And yeah, you see that very low way. Here in green it's simply the snake energy. In blue it's the novel energy we introduce here. And you can see that this energy is better than the snake in the sense that the minima of this energy are more easily, you can find them more easily. And they are better accentuated. So the first minimum here that is very important in the sense described before is B. It corresponds to this on this very simple image. That's the inner circle. We're working here on the tree of shape, so to dual. And the second important minimum here is the external. Okay, so the significant minima, well, it's easy to find the minima of this energy on the tree. It's a linear process, but you can order them and find objects in the tree, good curves in the tree, significant curve. Okay, so you can do filter with that. Filtering is simply you do a closing, meaning you remove, you get rid of spurious minima, and so you keep only the interesting minima, and it's a closing in the morphological sense. So you can do a closing with any kind of attribute. It generalizes also something called MSER, maximally stable extremal region. This is something well known in computer vision. It's something that find interesting shape in the image, and that they are used after that for doing kind of matching or registration of image. But the MSER are defined on the min tree, I think, or the max tree. So you can do MSER on the tree of shapes, so it's autodual, and you can use any kind of criterion. The one that is used in MSER is a ratio of area of nodes, but Okay, why not? It's a good criterion, but you can use any tree, any kind of attribute, and so do a lot of experiments with that. We haven't done those experiments, but you can, just the beginning, but okay. Okay. So, before showing some more examples, I just want to introduce saliency map, which is a kind of, well, we'll see. Well, from an image, you can obtain a set of segmentation. Here it's a simple segmentation, watershed, I believe, and merge the contours according to some criterion. Great. When you merge regions, you have less contours, but the nice thing is that the contours, they don't move. And so you can stack those contours. And the more the contour stays in the hierarchy, the longer it stays, the more visible it is. And you can see the more robust it is to variation, to change in the setting of your parameters. So this kind of map summarizes all segmentation depending on one parameters that you can obtain by varying the parameter. Okay, so there exists a nice theorem that says that these maps are equivalent to the dendrogram classically used in classification, and they condense all the information, and they can be defined as a kind of watershed, a specific kind of watershed. I will not go into detail here, but there is theory behind. Okay, so you can do some kind of saliency maps with the strategy I presented before, because you want to preserve blobs or remove blobs, whatever. You do that according to a criterion that was the altitude here, or the height, the depth of a basin. So the depth is a second criterion. You can see how long an object is persistent, and you can stack the contour of the object, and you have a summary of your hierarchy. And you simply weight the object's contour with the maximum persistence of the contour it belongs to. So, okay, here is an input image. Here is what you can do with the energy functional I've shown before. You can see that the three most visible contours are the one of the cars, military cars here, trucks and cars. You're missing here one part of the roof of this. It's not present here because it's too close to the background, but you have most of the cars anyway. Okay. So, some illustration. Okay, this is a leveling. I have a very simple image, which is nice to illustrate because it contains round, long object, round object, long object, and also you have white points here in the dice. And what else? Okay, a lot of stuff, but anyway, with a criterion, for example, filtering with round objects, it's easy. You just apply the strategy I've presented just before, and what you get is the long object, the one that are not round. Easy. If you make the difference, you obtain the round object. Okay, there is some objects that are less or more or less round than the other, but you can filter out what you want from the image. Okay, some beginning, not a full application, but just an illustration of the power of the method. To blood vessel segmentation in retinal image, we use the grid channel, first a black top hat transform to make the image straight. Then we apply the strategy, upper leveling based on circularity, and you just the connected component that stay at the end are the blood vessel. There is an available test base available online that is called Drive, with available ground truth, so you can measure how well you perform. And there are the performance measurement at sensitivity and specificity based on true positive and negative rate, accuracy, the rate of pixel correctly classified, and kappa value, which is a statistical measure of agreement between raters. Okay, so here is the first color image. You can look at the green channel that preserves most of the information. You make a black top hat, and you do a leveling on this image, and you obtain this kind of segmentation, which is very close to the manual segmentation. Okay. So here are some more examples, more or less difficult. You can see that there is the yellow spot here that is a bit disturbing, but basically these results look like they are a good step in the right direction. So you can have some measurement in black, in bold. This is our method, but there are plenty of others. And with a simple, very simple, now that you've understood it's very simple, simple filtering step, you can obtain something that is very close to the best results that are more complicated. The advanced method in this area use a number of other steps, but here it's just one filtering step that gives you a result that is usable, at least. You can see that you're below the expert, of course, but not so much. Okay, the nice thing is that it works in 3D also. You can extend that to 3D. So that first result, we are trying to do that to the same kind of process to segment coronary arteries in 3D. And with a simple filtering step, you obtain something that is not so bad. There are a lot of works behind, but this is a very promising first step in 3D. Okay. Another interesting point is the following. This is a detail, a crop of the first image I've shown at the beginning. When you have an image with two round blobs here, and you want to remove blobs, to preserve blobs, round blobs. Okay. This is the curve of the circularity, the evolution of circularity, starting from two different pixels, one taken here, one taken here. And you can see that the curves behave more or less in the same way, but they are not at the same level of circularity. So if you take a threshold, you can find on the blue curve, the spot you're interested in, the node you're interested in, but you have to take all the red curve. You cannot choose in the red curve. And that's the problem with thresholding. If you do thresholding, if your thresholding is not local, you have a problem. It's well known in image analysis. It's also true here. So if you do shaping, you choose this minimum and this minimum. B here, for example, correspond to this node, C correspond to this node, D correspond to this white spot here, and C correspond to this blue spot. And so the shaping I think, yeah, this is reverse probably. Yeah, so you can remove more or less detail. Yeah, if you, according to what you want to do, if you want to preserve B or not, Okay. So here are some results with different parameter setting. The image, a shaping based on first attribute, and 2 thresholds of the same attribute compared to the shaping. So what can you see? What can you notice on the image? Yeah. Sorry. Is that in the background here with thresholding, you have a lot of noise in the background that you don't want. Here you have less noise in the background. Well, it's also true within the shape themselves. For example, this shape is missed with a low threshold. You have it with a higher threshold here, but you have more noise in the background also. So here it's a compromise between the two, and the result is not so bad as a first filtering step. Well, it's easy. A nice thing in the process also is that it's very easy to use any kind of attribute. So here it's 2 different roundness attribute, and you can go a bit further and obtain a cleaner image by using different roundness attribute. Yeah, circularity and the first 2 I've shown in the beginning that measure how round a shape is. So this is a very clean result here. Okay, here are some results of using the energy. Within red, the object detected. You can see them. You have seen them on the silency map, but here you just take a threshold of this tree, and you obtain 3 regions. That's what you want, the most salient one. Okay. You can do object detection also, simply using the attributes, the roundness attribute. In red, this is based on circularity. In green, it's based on inverse of the elongation attribute. But you locate your objects, and you can classify them using this kind of filter. Okay. Here is another example application, which is the optic nerve segmentation, the disc you find in the eye. This time we use the red channel because it's there that you find the information. A small closing by a disc, then the tree of shape with a specific attribute, and you just found the best best fitting ellipse. It will give you the disc. There is also a database on which you can evaluate the result according to discrepancy. But here the kind of result you can obtain with a disc here located in which is very close to the manual result here on this example, of course. Here are some more examples. The discs are good here, but the method is not always good. Here are the result of the evaluation. You can see that we are better than some of the method, but lower than the 2 best methods existing on the market. But once again, this is a simple filtering step, and I think the result can be enhanced by using more processing step. In the other method, they used anchor points, and based on those points, they do some other stuff. So I expect that with the image filtered, in which the result is there, hopefully, it's easier to apply more post-processing step to obtain a better results. But here, we stop just here. Well, there is the accumulated discrepancy, but I will not describe that. Okay. What else can we do with that? 2 more examples I will describe. If I have time, yes, I do. The first one is image simplification. It's not filtering, not exactly filtering. You start from a given image and you just want to obtain an image that is a simplified version of the original one. So you can start with the cartoon model, in which you measure the variance and the length of the perimeter. And you have a parameter nu here, which measures the simplification level. And actually what you want to do is reverse the equation, extract nu, and so you can build the tree of shapes, weight each node with nu that you can compute by reversing the equation, and computer saliency map, which provide you a hierarchical simplification. This is very fast, and this provide very good results actually. So is an original image. You have the saliency map in which you can see that the contours of the original image are preserved, and here is just one level of simplification close to the original image but with much less detail. Some other examples. Once again, this is a choice between all the possible levels. How can you do the choice? It depends on what you want to transmit, for example, bandwidth reduction. Here is image of a bird, in which you have a simplified version, which is not so far from the original. Here, this image. I do like the saliency map of this one. It's very pretty, I think. Like a drawing someone will do manually. But then again, the simplified version is simplified, but you lose some texture information, but okay. Well, we haven't evaluated this method yet. I don't know exactly what we can measure on that result, but we'll find something to assess the quality of the result. Here it's a complicated method. You lose completely the texture, the lines here, but basically you found the two regions. And you can do the same on the military image. Here the saliency map is quite different, but you obtain a good simplified image which contains what you want exactly. So you can post-process this image also. Okay. Another example is the classical algorithm. You probably know this algorithm, this Wenzel-Schwab and Utellencher algorithm. I'm so difficulty telling the name of these two people. Well, the algorithm is very simple. They compute a minimum spanning tree of a given dissimilarity, which is here it can be a simple gradient, for example. And for each edge of the maximum spanning of the minimum spanning tree, they look at the region that contain X, the region that contain Y, and they merge the two regions if this rule is satisfied. So basically, here it's a measure of how the contrast inside the region. Here it's the number, the size. So you don't want big regions, and you don't want them to be too contrasted. There is too much contrast in the region. Well, this method is well known, very popular in computer vision. The problem is that K is not a scale parameter because it violates, for example, the causality principle. I mean, when you move K, you don't control whether the number of regions goes down or goes up. You don't know. So when you change K, you can have very different results, and it's difficult to set up the correct parameter for the method. But it works well once you have set up the parameter. It gives you good regions. So you can make transform K into an attribute by reversing the formula. It will give you that max of the difference of this formula. Okay, whatever it is, it's not very important, but it's the same attribute, same formula. So you can plug it into the framework, and here you have a hierarchical method. So how do you do that? You just compute a minimum spanning tree of a distance between pixels, or color distance, or gradient distance. You build a minimum spanning tree that is a hierarchical transform of your image. You have ordered the pixel according to a tree, to a hierarchical tree, which is the minimum spanning tree. For each region in this hierarchical family, you compute K, and then you compute the saliency map, and okay, you can evaluate. You can evaluate because there is an evaluation provided by Arbelaez, which is a collaborator of Malik, and they provided some way to evaluate hierarchical methods or segmentation method. Actually, it's very critical. There is a lot of critiques that can be formulated because it's very hard to evaluate segmentation. But anyway, this is they have provided something so you can look at the results. So it's on Berkeley. I don't remember if this is from Berkeley, I think. You can look at the saliency map of the FH criterion and choose a number of regions. Okay, that's more or less what we did with Fortune. Okay, another example. You see that the most important lines, contours, they are present in the image. And if you choose correctly a good level, you can find the object of the scene. Here is the bird example. Okay, so here is the first result of the evaluation. They have to be taken with care because there are a number of parameters that can be tuned here, meaning that, for example, the first one is on which energy, on which distance are you computing the first minimum spanning tree. You can make a Gaussian convolution on the original image that give you one parameter. So there are a number of steps, but anyway, the FH method give you this result here, and our result with the same method is better. I'm not sure. Well, once again, this has to be taken with care. For information, I've added another method for transforming this method into hierarchical approach. This has been done with Silvio Guimaraes and colleagues at ESIEE. So this is for advertising. Here, Silvio just spent 1 year at ESIEE, and we have worked together. So you are welcome if you want to come. But once again, the evaluation are not definitive. So maybe this method is better. Maybe we're not completely sure. But they can be evaluated. So, some conclusion. Well, this is a new filtering that unlock one of the difficulty of previous connected filters. In previous connected filtering strategy, you had to use an increasing attribute or to do some kind of thresholding, which is not satisfying. Here, by transforming your image, you start from an image, you just transform it into another graph, and you apply morphology on this graph. Whatever it is, here it's trees, and you deal with the graph and you transform it. You can do whatever you want simply by changing the space you're working on. So we have seen two applications: object filtering, which is a generalization of the state of the art, and which allow us to propose new kind of filters, based on shape-based leveling and morphological shapings. We have also done some application to object detection using context-based estimator energy or specific attributes that are designed on the fly. For example, the attribute for the optic nerve segmentation, it's something like it's more or less round, it's more or less in the center. Those kind of information that can be put into the energy and look at the results, very easy. And you can assess the quality, the robustness of the parameters, building a saliency map to see if by changing more or less by tuning differently your parameters, the method vary a lot or not, so the robustness of the parameter can be seen on the saliency map. So basically this is what we've done in this work. There are a lot more things that can be done, especially looking at different attributes. What's the difference between the attribute on the first tree or the attribute on the second tree? Something that I find very promising is to learn the attribute. Here we use for roundness some very classical measure, but maybe you can learn what is round from examples. And in that case, it's totally automated. You don't choose, you just learn to choose the right curves. Maybe also there exists different strategy for dealing with the second tree. So this has to be explored. We want also to study more mathematical properties of the morphological shapings, see exactly how they can be characterized, and use the saliency map. Well, since I have a bit of time, I will show you a short demonstration just after this last slide. This slide is for advertising. Once again, there exists a very good book that has been edited by a colleague and myself that does not contain this kind of stuff, of course, because this is very recent, but it's contain a lot of things on mathematical morphology, and it's by with ISTE Willet. There are two kinds of software that you can download and use yourself. They are open source and available online. The first one is Pink, which Pink is the acronym for Pink is not Chorus. For those of you who knew Chorus, it's recursive acronym. So in Pink you find all the algorithms that have been developed in the last years, in the 20 last years at ESIEE, except maybe what you found, what I presented today. What I presented today is, you can find that in Olena, maybe not yet, but in the next release. Olena is a generic environment, generic image processing tool that is developed by Thierry Géraud at EPITA, at the LRDA. It's genericity. What is the meaning of genericity? Well, you all know what an image is. An image can be seen as a graph. You have neighbors, but when you want to, for example, pass from 2D to 3D, you have to write again all your algorithms. It's very difficult to change something. Well, in Olena, everything is written in a kind of using template, kind of template adapted to image processing. And so the compiler does the job for you. Once you've described what a neighbor is, you can work on any type of graph, and the compiler will translate what you want into the code you would have written by yourself. So it is very efficient, very, I mean that you can obtain the same speed that with the original, if you write a dedicated code, if you give to the compiler enough information. For example, you work on a 2D grid with 4 neighbors. The compiler will provide the right code, but it can also provide the code to work on a generic graph. And what I've shown here is I have applied the mathematical morphology on a generic graph. Actually, I built the first graph using a dedicated algorithm on, for example, on 2D with 4 neighbors. But then, if I want to work on the tree produced by the first algorithm, I have to program everything again, but not with Olena. I just compile a new stuff and you apply the algorithm. You don't have to write anything. So you can, these two, there are more algorithms here, but this one is more promising. They compete together and they are developed by different people, but I'm involved in the two teams, so okay, we'll see. And just for conclusion, let me see a very simple example. The screen is too small, so you don't see. Actually, here there are a lot of attributes, and when you click on one point here in the image somewhere, you have the curve of the attribute from the root, from the pixel to the root. So this is very convenient to choosing what kind of attribute you want, or the parameter. I will show you that. This is an X-ray image, and actually they are, the person that undergoes X-ray has a lot of things inside the body. I don't know exactly what they are, but they are left by the doctor, so I suppose they are useful for living. But that's rather strange to have that in the body. But anyway, here this is the tool of that something that you may want to extract, for example. So you can click here, and inside, this is inside. I'll just go a bit inside here, just to be sure. Maybe more. Okay, I click here. In the, and then you can look at the component here. The component here, this is exactly what you want. So you can estimate from here the depth of here. It's a very simple energy. It's the gradient along the contour, the mean of the gradient along the contour, and you can see that it works very well here. Here it's the ratio. The ratio here is good also. You can see very quickly you obtain the more stuff. But basically, here the other, some of the other attributes, they don't work so well. Of course, you don't. The circle here works, but it's a maxima, it's not a minima, so it's very strange. You can't use that. The RR is not working, so you can tune your parameters using that kind of interface, and then produce the whole filtering. Of course, you will obtain when not only this object, but other objects. So you have to be careful. But actually, you can see how robust or not. I'm not in the right place. How robust or not the energy is. So here the deepest minimum is this one. It marks all here, but actually you will obtain the other by the other direction, I believe. Okay, so you can see if it's robust or not. And actually here, the minimum here is very deep and bright here, so it's very robust. And so you can extract those kind of tools very easily with just one filtering step. Well, thank you for your attention, and I welcome questions.
Any questions?
Who will be the first one? Thanks, Alexander.
Thanks, Laurent. I appreciate the talk. It was very nice. As far as I understood, that when you build this tree of shapes,
yeah.
So it's always the strategy to convert that into some minimal component tree, like min tree or max tree. So if it's the strategy, then you can only deal with one attribute per node of the tree of shapes, or could you extend that for multiple attributes, for example?
In the strategy we have proposed there, the way to deal with multiple attributes is to combine them in a unique formula, like an energy formulation, for example, with parameters. And of course, this may not be satisfying, but this is the classical way to deal with level set, for example. And so there is a lot of experience from level sets that can be transferred to that framework. And this is a very good question, because the next step is to deal with different strategies, so different trees, for example, lattice of tree, and try to combine the best information from the lattice. But we don't know exactly how to do that now. We have some ideas, but...
Now, I like the idea of applying a functional to the nodes of the tree of shapes. I think it's a clever idea to incorporate more complex, let's say, energy, right?
Yeah.
The other thing is that, have you thought of using some kind of object model for the last part, for example? Or you could apply that maybe after, over the mean tree, for example.
Yeah, for example, yeah, of course, this is, the attribute is just that, object model. The one I've presented, they are not learned. They are just either an energy function, either attribute like roundness or compactness or whatever. But I imagine that you can, for example, you give to a bunch of students or experts, depending on the situation, they draw what they want, simply lines, black and white. They take a pen and they draw what they want on the sheet of papers, and you can learn to recognize curve. And then you just plug that into the framework, and you will recognize the right curve, the best one among the set of curves you're studying. Yeah. And this should be very interesting to do also.
Yeah, I found that very, okay, that's nice.
Thank you.
Thank you, congratulations.
Thank you very much.
Any more questions? Okay, I mean, this is a very, very nice, comprehensive talk of all your work that you have done over a period of time, and looks like it's a very powerful method. A simple idea you've built on, applies on various domains. Now, one of the sensors that's very popular these days is the Microsoft Kinect sensor.
Yes.
Gives you depth. So, do you see some of these ideas being can be applied to those kind of depth data, to clean up, to detect things?
Probably. I haven't thought of that yet, but basically this kind of method can be applied on any kind of depth image, for example, to look at what you want to find, if they are visible in the image. And so probably, probably they are
applicable.
That's applicable, yes.
Thank you, because those data is very, very noisy, and they are not, I mean, they have holes in there, so some of the ideas that you're talking about should work pretty well.
You can process any kind of data like that, and just if you can design a criterion that will find what you want, hopefully, normally you should obtain something. I hope so.
That's good. Thank you. Any other questions? Well, thank you. Thank you, Dr. Najman.
Thank you very much.